So, welcome back to our video lecture on projective geometry. In this part of our class we are still dealing with conics, and today we will learn about the concepts of polarity and duality in relation to conics. So we know everything in projective geometry is somehow a dual theory. So points can be interchanged with lines, joints can be interchanged with meets, and the question is, what does this mean for conics? And we will dive into that during this video slot. So to do so, we start at some seemingly different end. We are dealing with the so-called polarity operation. So what is a polarity? So let me start with our definition of conic that we had. We defined conics as a solution of quadratic equations, and we expressed that nicely by considering this matrix equation. So a conic was given by a symmetric matrix A, and a point is on that conic if this quadratic equation here is satisfied. So we have this equation. And now we will have a closer look at this equation, and we will deal with the question, what is this part of the equation here? So we have a matrix times a point. This looks a little bit like a projective transformation, but it is a kind of line-like object because it's multiplied with a point here. And so we will, well, in detail now study the geometric meaning of this product. And to do so, we will define a mapping that takes a point and maps it to the coordinates that we get by A times the homogeneous coordinates of the point. But as an important ingredient, we will consider this new object here as a line. So we start with a point, multiply by a matrix, and get a line. And the question is, where is this line? And so what we know so far is that this line here has to go through the point, because the scalar product of the point with the line turns out to be 0. So we know it must look somehow like that. So it must be a line through our point. But I already tell you now, this here is the wrong position. So we will be asking whether this line here is the correct position of our mapping, and it turns out it is not. And actually it will turn out that this line that we get here is actually tangent to the conic as well. So the true position will be something like that, and we will prove that in a minute. We will do this proof in the following way. We will assume on the contrary that it is not tangent. Being not tangent means that there is a second intersection of the line with the conic. Let's assume that this second intersection is named Q. So, and now we will prove that the only way that this can happen is that P and Q coincides. And for that we will show that if we know that both P and Q have the property of lying on the line and on the conic, then all points of the line has to lie on the conic as well. And this would mean that our conic should be degenerate, but over here we said we want to have a non-degenerate conic. So let us have a closer look at the line connecting those 2 points, and for that we first collect things we know about these 2 points here. So first thing we know is that actually P is on the conic. So we know that P transposed AP has to be 0. Second thing we know is that Q is on that line, so that Q is coincident with A times P, which can be written as Q transpose times A times P has to be equal 0 as well. And third thing we assumed is that Q itself is on the conic, so we also know that equation. And now we are doing linear combinations of these equations, and for that we choose a generic lambda and mu, and later on we will consider the linear combination of lambda p plus mu times q, which will be just some generic point on this line. And we will prove that this point also has to be on the conic. So to do so, we first combine our first two equations here. You see they are similar in this second part here, so, and they are linear, so we can form a linear combination of those 2 points and put them here and still obtain a 0. In the same way, we can combine the last two equations, say agree in the first part, and we can replace the p and q by a linear combination of p and q. Now if you look at those equations, you can reformulate one of them by reversing the order of the factors, and then see that this factor linear combination times a occurs in both equations. So you can again make a linear combination between these 2 points, and what you end up with is this equation. And if you look at it, it is the equation of a point lying on a conic. And what point is it that lies on the conic? Well, it's our generic point on the line connecting P and Q, which proves that the entire line must coincide with the conic. And well, if our conic is non-degenerate, the only way that the linear combination of P and Q can be on the conic is that P and Q have to coincide. So we just proved that there is no other point except of P lying on the conic, which means that we really get a tangent. So let's call this a theorem. If we consider our mapping star A and map our point P, we get a line that goes through P and is tangent to the conic. So we have a nice way of constructing the tangents through a point on the conic by simply multiplying with the matrix A. So you see, by this operation we associate every point here with a line which we would call the polar of this line with respect to P. And actually this is a one-to-one relation, because our matrix A was chosen to be non-degenerate, which in turn means that also the reverse of our mapping makes sense, and we extend our polarity mapping in the other direction, and we define the polar of the line to be the point that mapped to that line, and we simply can get that by multiplying the line coordinates with the inverse of our matrix. After all, we can say that if we call this line here L, then the polar of this line is our original point P. So after all, we got a one-to-one correspondence of points and lines through a matrix of a conic, and we may ask what happens if our point P, for instance, is not on the conic. And for that we first need another interesting and small theorem. The mapping that we have here, it preserves incidences. So if a point and a line were incident before the mapping, so assume you have a point and you have a line through that, and then you make a polarity mapping, then the point turns into a line and the line turns into a point, but incidences are indeed preserved. And this is a pretty simple calculation. So assume that a point is incident to a line, then we can rewrite this as well, the point transposed times the line equals to 0. We can slip in unit matrix by slipping in A times A inverse. We can reformulate that by taking the transpose of A instead of A, because A was a symmetric matrix. And if we did so, then we see that we can reformulate it as an incidence of those two points. So we collect those two objects into one entity, and we collect the other two objects in a second entity. And these are actually the mappings of P and L under our star map, and we see that they have to be coincident as well. So we know several things now about our mapping. We know that it is an incidence preserving map. We just proved that. We know that if we have a point on a conic, then this map creates the tangent of that point. And conversely, if we have the tangent to the conic, it will create the point of intersection. And this can now be used to calculate the position of a line that is the polar of a point P if P is not on the conic. So how to do that? Well, we can use our three facts that we have. So first of all, draw two tangents through our point P to the conic, and you will get those two lines. They just have some position. And now you know these are tangents, and the polarity operation for the tangents gives you these two points of intersection of the line with the conic. But you also know that our map is incidence preserving. This means that if our two lines intersected at a point P, the join of those two points here must be the polar of our point P. And so this is a nice geometric way to reconstruct the polar of a point P from just geometric considerations. And you may ask, what happens if our point here actually lies inside the conic? So assume you have a conic and you have a point P that is inside the conic, and then it's difficult to apply this procedure here. There are two ways out of that dilemma. First of all is extend the field. So this point here has still some tangents. They are just complex. And you can calculate them, you can intersect them with the conic, you will get two complex points, but it will turn out their join will be real again, and you will get a line that looks more or less like that. There is another way of doing that by doing a slightly more extended geometric construction. I give it to you as an exercise to figure out what construction that is. So now let's come to a little bit more abstract things, and let's consider the set of all tangents to a conic. So here I've drawn two pictures. So assume you have a conic, say an ellipse here, and you are interested in a nice description of the set of all the tangents to that conic. Here you have a second picture, all the tangents to a hyperbola. How can we calculate that? And actually, polarity helps a lot to calculate these sets of lines. So let's start with something we know. The set of lines that we are looking for comes from all possible points on the conic and applying our polarity map to them. So take a point on the conic, multiply it with the matrix, and you get one of the tangent lines. So you get all of the tangent lines if you take all the points of the conic. So now we will slightly reformulate what we have by again slipping in a unit matrix here and reshuffling our vectors. So what do we have here? We have this expression, and we can rewrite it once more by replacing A by its transpose, because A was assumed to be a symmetric matrix. But if we do so, this here is an equation of two entities A times P. And A times P was our line. So now we get an equation for our line. So we see that a line that is tangent to the conic has to satisfy the equation line transposed times A to the minus 1 times line has to be 0. So this gives us a description of what people call the dual conic. So the primal conic consists of all points on the conic, and the dual conic consists of all the lines that are tangent to the conic, and we can get that by simply replacing A by its inverse. So a conic in a dual theory really consists of two things. So on the one hand, we have all points on that conic, and in a dual way, we have all lines simultaneously tangent to that conic. And the rest of that lecture will deal with the question of how are primals and duals related, and we already know it for this case here. So we just have a non-degenerate conic here, and we see in the case of a non-degenerate conic, the corresponding dual conic is given by the inverse of the matrix. So this only makes sense for non-degenerate conics, because only in the case of non-degenerate conics we can calculate the inverse. Let's see if we can get rid of that. And for doing so, here is a little observation. There is a nice matrix operation which is called the adjoint of a matrix, which is a certain, well, seemingly complicated expression. So it looks like that here. And if you start with a matrix A and you calculate the adjoint, you take all 2 by 2 submatrices, distribute them in the right way in a matrix, and assign them with pluses and minuses in a checkerboard-like way. And it turns out that this matrix here is nothing else as the inverse times the determinant of the matrix. So it's up to a scalar factor, the same thing as the inverse matrix. And we didn't care about scalar factors because we have a homogeneous theory. So at the end, we can simply replace our matrix A here with the corresponding adjoint. So let's move this equation out and let's move a different equation in where we replaced our inverse matrix by the adjoint matrix. What did we gain? Well, we gained one important thing: we don't have to divide. So if you calculate the inverse of a matrix, you do more or less the following thing. You calculate the adjoint and divide by the determinant. But we do not care about scalar factors, so we can simply omit this dividing step and have a formula that even makes sense if A is a degenerate matrix. So we still can calculate the adjoint even if A is degenerate. And let's see what happens here. So let's assume that we are in the situation that A represents a degenerate matrix. So A can be decomposed into two lines, and we get a matrix that we already saw that, can be calculated by multiplying the two lines together and symmetrizing. So the question is, what is the adjoint of that matrix? And it turns out that the adjoint of that matrix is nothing else as the cross product of the two lines, which is the intersecting point, multiplied by its own transpose. So you get a matrix, and with a minus in front of that. Well, we don't really care about scalar multiples, so let's forget about this minus. So for a suitable representation of our point of intersection here, the adjoint here turns out to be a rank 1 matrix that you get from multiplying the point by itself. I won't prove that formula here. If you really want to know why it's true, well, the simplest thing you could do, simply plug in the coordinates in the two expressions and compare term by term that this is really the case. So it's really not a deep mathematical equation. You can simply check it by calculating. So what does this mean? This means that if you start with a degenerate matrix, you end up as a polar with a rank 1 matrix that is described by the point here. So you get a kind of, well, double point at point P, which represents the polar. And I will tell you in a minute that this indeed makes sense. Before we do that, let's have a short view to the rank 1 case. So the rank 1 case, you have already two lines coinciding, and you have a rank 1 matrix here. And if you calculate the adjoint of a rank 1 matrix, you will get the 0 matrix. What does this mean? This means that in that case, you cannot get the polar from just calculating the adjoint. You just have too little information. We will see what this means in a minute. So let's first have a look at this situation, and I've drawn all the tangents of our conic A that we get, and actually all the tangents accumulate at this one point P. So essentially it makes sense to say that all the lines that go through point P are encoding the polar of our matrix. So if you don't believe that, here is a little more elaborate explanation that shows how you get from a non-degenerate situation to this kind of double point and get back to a non-degenerate situation. So assume you start with a hyperbola and make it steeper and steeper until you get to the situation where you just have two lines. And if you look at the tangents to your object, you see that in the limit case, what you actually get is a whole bunch of lines through this one single point. So it really makes sense that in that case, the polar is considered to be this one single point, which has to be counted as a double point in that situation. So let's look at the rank 1 situation, what's happening there. And what I claim is that the dual is not already determined by the equation we have here. And for that, let's take a picture from Felix Klein's lectures on non-Euclidean geometry, which were published in 1928 after the death of Klein, unfortunately. So here we see a transition of an ellipse getting thinner and thinner until it's kind of a double, very, very, very thin double ellipse, which has still two endpoints. And if you continue this parameter, you will get a situation where you have a double line as well, deforming into a hyperbola. Here I wrote down the equation of that formula. So you have a parameter a going from -1 to +1, and when a is 0, you really get a double line here. let's look at the tensions that you get here. And this picture is also taken from Klein's book. The tensions look as follows. Well, in the limit case, and that's an interesting case for us, the tensions here accumulate around 2 points, no matter whether approach from this direction or you approach from this direction. So actually the dual conic here consists of 2 points on a line. This double line here is the line that we observe in these pictures, but it doesn't have enough information to tell you at which positions these 2 points are. And this is the reason why we get a 0 here. And if you look at it, it's just dual to the situation that we had when we studied degenerate conics in the primal case. A primal case was 2 lines together with a double point on it. And in the dual case, we have 2 points together with a double line through them. So it's really literally just the dual, and the dual degenerate conic may consist of 2 points with 2 lines through them. So let me more or less sum up what we got so far. So we have a notion of a primal conic, and we have a notion of a dual conic. And in many cases, the primal already determines the dual, but not in all cases. And conversely, in many cases, the dual already determines the primal. And this is the situation that we have. So let's make a kind of table consisting of the primal conic given by a matrix and the dual conic given by a second matrix. And let's try to draw a picture of what's going on. So it could happen that our matrix here is a rank 3 matrix. So we have a non-degenerate conic, and we know that our dual conic is represented by some multiple of the inverse of matrix A, which is nothing else as some multiple of the adjoint of this matrix. So essentially we can get matrix B by calculating the adjoint of A and, well, some multiple between them, which doesn't care. And we can go also the other way around, and if we have matrix B, it will also be non-degenerate. We can get matrix A, so this is a two-way road corresponding to a non-degenerate conic. So it could happen that A is rank 2. That means it decomposes into 2 lines. So then still we can get the matrix B by calculating the adjoint of A. So we can get from here to here, but we cannot get back because B is already rank 1, the double point that we see here. And so calculating the adjoint here would not give us matrix A, it would give us a 0 multiple of matrix A. The converse could happen as well. It may happen that B is rank 2 and A is rank 1. This would be the case when we have a double line, A is rank 1, with 2 points on them. And from those 2 points, we obviously can calculate the rank 1 matrix, which is the double line through these 2 points. So this time it goes in this direction. And it may even happen that we have rank 1 on both sides. And in this situation, we can neither go from A to B nor from B to A. What we have is a double line with a double point on it. And so in that case, neither the primal nor the dual carries enough information to calculate the counterpart. To make the situation a little bit clearer, I also added the tensions to this drawing. So here you see non-degeneracy in both cases. Here you see all the tensions go through 1 point. Here you see the tensions accumulate in 2 points, and here again all the tangents go in 1 point. So let me go one last step further and then we're done with this lecture. You remember we made a classification of conics in one of the previous lectures, and there we really distinguished between complex cases and non-complex cases depending on the signature of the eigenvalues of our matrices that we get here. And this in turn leads to a further subdivision of our classes that we have here, and what we actually get is this classification. So the first 3 cases also have a kind of complex counterpart. I marked the complex things with red lines or red points. So in the first situation of a non-degenerate conic, you can get either a real non-degenerate conic or a complex non-degenerate conic. In the second case of 2 lines, these lines are either both real or they are complex conjugates. And in case of complex conjugates, their intersection is still a real double point. Then for this case here, we get this dual situation. We have 2 points which either can be both real or they can be complex conjugates. And in both cases, the line joining them will be again real. And in the last situation, you will get a real point on a real line, both of them double points respectively, double lines. And up to projective equivalence, these are exactly the 7 cases of pairs of primal and dual conics that you can get in the classification of conics. So whenever you have a conic, and now I mean a conic in the general sense consisting of a primal matrix and a dual matrix, you will up to projective transformation end up in one of those 7 cases, and we will later on see that these 7 cases give us a classification of possible so-called Cayley-Klein geometries, which give us matrix geometries where we can really measure embedded in complex planes. And those of you who already attended the Geometriekalküle lecture will notice that this case here corresponds to the Euclidean geometry. Let me finish with one nice characterization of when A and B forms a suitable pair of primal dual matrix. I won't prove that here. You can read the proof in the Perspectives on Projective Geometry book. A nice characterization of A and B being a primal dual pair is the following. If you multiply A and B and you get something that is a multiple of the unit matrix, then they form a primal dual pair. So let's just look for a moment at the first case. So here A and B are essentially matrix and its inverse up to scalar factor, and what you get here is really, well, something like lambda times the unit matrix. In the other cases, you will always get the zero matrix, which is also a multiple of the unit matrix, a zero multiple. But the fact that you get this multiple of the unit matrix is exactly encoded in that equation. So far, this was a quite, well, theoretical slot on the relation of primals and duals and polarity. We will use all of that in later video lectures when we, for instance, enter in the realm of Cayley-Klein geometries. I already showed you that here. A second topic where this becomes relevant is when we do primitive operations of intersecting conics with lines, and this is what we will do in our next video lecture. See you there!